Okay, calculus, let's talk 10.2, an intro to parametric equations. Well, I'm going to do things from page 1 to 3. Page 4 and 5 are really more interesting applications of parametric equations that you might enjoy reading about. There's no actual problems. So a parametric equation is basically, we have equations that are rectangular where y depends on x, but it's having x and y depend on a separate variable, often t for time. The reason we do that is first off, it lets our x and y be functions when they may not be otherwise, so x can go back to things, but it also takes a shape and creates a travel pattern. So normally if you have a parabola, you just have a parabola, but parametric equations can give you a direction you are traveling on the parabola. For example, taking this rectangular equation, y equals negative 1/72 x squared plus x, and x equals 48 cosine theta t, and y is 48 sine theta t, minus 16t squared, produce the same shape, but one of them gives the pattern of an object flying on that parabola launched from 0, and the other one doesn't. Now, to graph a parametric equation is pretty easy. You just plug in the same t to both x and y, and you plot the point x, y. Let's see how this works on the first problem. Sketch the curve on the interval from -2 to 3 for t. X is t squared minus 4, y is t over 2. So let's make a chart from -2 to 3 and find what our x and y is. If I plug in -2 here, 4 minus 4 is 0. For y, it's t over 2, so -2 over 2, which is -1. At -1, that would be 1 minus 4, which is -3. Y is -1/2. X for 0, 0 minus 4 is -4, y is 0. You plug in 1, it's again -3, and now +1/2. And we're back at 0 and +1, and at 3 we're finally at 5 3/2. And we can take those and plot them and see what happens. So we have 0, -1, -3, -1/2, so that's about here, -4, 0, -3, +1/2, so the same thing above, 0, +1, and 1, 2, 3, 4, 5 3/2. So we have this, looks like a sideways parabola. Not only do we have a sideways parabola, though, we can kind of have a direction and draw arrows for the way we're traveling here based on time. Assuming time is increasing, we are going this way across the parabola. So we're traveling along this parabola in a direction. That's something that parametric equations can do that rectangular ones cannot really do. You don't really have a direction for rectangular coordinates and their comparisons. Now, could we have gotten this shape some other way? Yes. If we let y equal t over 2, all we have to do is solve for t and substitute y into the other equation. So that means 2y equals t. So if x equals t squared minus 4, and we substitute 2y in, we get x equals 2y squared minus 4. Well, 2y squared is just 4y squared minus 4. And that actually represents the parabola. The only thing we'd have to do there is we'd have to restrict. We'd have to say y is between, if we're going to let y be the parameter, we know y is between, it's bigger than -1 and it's less than 3/2 in order to restrict ourselves to this. And while this wouldn't give us the direction, it kind of does if we go based on y. If y starts at -1 and goes to 3/2, it does follow the same pattern. We just have to be careful with the directionality of that. So that's page 1 and the first example on page 2. We'll do the rest of the examples on page 2 and 3, though I did make a change to the second problem on page 3 after this. And and we'll just go from there. Maybe a pretty short day.